Today, we will be discussing the fifth lab of Physics 2211. In this lab, we were asked to find our own venture. So I am combining Lab 2 and Lab 4 to investigate the energy of a falling object. The objective of this lab was to observe a real-life example of an object dropped from rest, and to apply Newton's second law of motion and the energy principle to understand the effect of force of gravity and the effect of force of drag on the energy. The motion I observed was an ice pack being dropped from rest and falling to the ground. Then I created a computational model using GlowScript that depicted the motion of the ice pack, with and without drag force. The computational model and experimental model were compared to understand the effect of drag force on an object and energy. My results show that the computational model data that includes drag force shows a higher correlation to the experimental data than the computational model data without drag force, as the graph shows the data points deviating from the experimental data near the end of the time frames. Also, the energy graphs begin to decrease in the drag force model, while the model without the drag, the energy remains constant. The fundamental principles that were used in this lab were Newton's second law and the energy principle. Newton's second law is force equals mass times acceleration. This can be derived further into the equation. The final velocity is equal to the initial velocity plus net force divided by the mass times delta t. This equation is used to find the final velocity after a change in time. The computational model uses this equation to update the final velocity as it runs through the program. Derived from this equation is a position equation, which the computational model uses to update the position of the ice pack as the program runs. The energy principle states that energy cannot be created nor destroyed. The energy principle states that energy cannot be created nor destroyed. The change in energy is equal to the change in kinetic energy plus the change in potential energy. Kinetic energy is equal to 1/2 mass times velocity squared. The gravitational potential energy is equal to mass times gravity times the change in distance. This is the recording of the ice pack falling. The object moves down the screen in the negative y direction. Tracker plots a position versus time graph on the upper right-hand corner of the screen. The plotted points are seen to be curving since we know that the slope of the position versus time graph is velocity. The ball is traveling with a change in velocity, meaning F net does not equal to 0. Below the graph is a table of position and time points, which are points that I use to plot the experimental data. Using the data that I obtained from the video analysis and tracker, I completed simple calculations that will be used in our code when creating a computational model. The mass is equal to 1.98 kilograms, which I found by using a scale. The start time is 0 seconds, the final time is 0.667 seconds. The initial position is 0 meters in the x, y, and z direction, as the origin was set to where the ice pack was dropped from. The final position is negative 2.0192 meters in the y direction. The initial velocity is equal to 0 in the x, y, and z direction as the ball was dropped from rest. The proportionality constant for the magnitude of drag force is equal to 0.2143. This was found by trial and error by choosing values and checking if the final position value of the computational data equaled the final position value of the experimental data. We start the code with basic initializations. Here we plug in the ball's mass, ball's initial position, initial velocity, and start time. Then the code has further initializations. Delta t is set to be a small number value so we can receive more accurate results. I have inputted the gravitational constant, 9.8, the drag constant, and the code for the kinetic energy and gravitational potential energy. Now the code initializes the energy values so we can calculate the energy changes as the object falls. This loop will update the position of the model using Newton's second law. Here is the code that represents Newton's second law. Notice that F net is equal to the drag force plus the weight force. Drag force is calculated by multiplying b by the magnitude of velocity squared. Every time the code loops through the initial velocity will be updated in order to find the new position at a given time, which represents a shift in the ball's position. The energy changes I found by calculating the new energy values with the new velocity and positions, then subtracting them from the initial energy values. This is done here for the kinetic energy and the gravitational potential energy. These values are added together to get the total energy and the total change in energy. Then the code has these values plotted onto the graph. We ran the code twice to show the different energies of the falling object with drag and without drag. On the graph, the blue line represents a change in kinetic energy, the red line represents a change in gravitational potential energy, and the yellow line shows a change in total energy. In the model without drag, as kinetic energy increases, the potential energy decreases. The change in total energy of the system remains 0 throughout the motion. In the model with drag, all of the energies began to curve. I ran the code for a longer period of time to see the full effect of drag on the energies, and I will show you the graph later in the video. This graph shows the experimental data that was obtained from the video analysis and tracker, and the computational model data that includes both data sets with only weight force and a data set with both drag force and weight force. The orange line represents the computational model with drag force, and the gray line represents the data without drag force. The computational model data with only weight force deviates from the experimental data near the end of the time frames. This is due to the fact that our object did not only interact with the weight force, but also drag force. The correlation of the computational model with data and our experimental data is very strong, as they line up almost exactly. Any deviation can be due to the fact that the drag force constant is not the exact constant that represents the experimental data, as we use trial and error to find the close approximate. Also, this can be due to the fact that the object was blurred when plotting the points in Tracker. Therefore, the center of the blur was used, so it is not the most accurate representation of the object's position. Here is the energy graph with drag. The kinetic energy increases then decreases until at zero. This is due to the fact that the object experiences terminal velocity, so the change in kinetic energy will become zero. The change in potential energy curves in the negative y direction, because at terminal velocity, the change in displacement over the change in time is constant. Therefore, it reaches a constant negative number at terminal velocity. Therefore, the total change in energy will begin to equal the change in potential energy, as Ke will become zero. Is the energy principle satisfied? Yes and no. In the model without drag, the energy principle is satisfied, as the change in total energy was equal to zero, as there was no external forces acting on the system. Our computational model supports this conclusion, as the yellow line representing the change in total energy was equal to zero constantly through the entire motion. Therefore, there was no energy gained or lost from the system, which satisfies the energy principle. In the model with drag, the energy principle was not satisfied, as the change in total energy was not equal to zero, as there was an external force acting on the system, which was drag.